So on with tonight's monthly meeting of the Nottingham Astronomical Society, and our lecture this evening is on variable stars and will be presented by Dr. Jeremy Shears, who I'll introduce to you shortly. Before we start then, just a quick update on our forthcoming meeting schedule. We've now planned in 2 further online meetings, so our next meeting will be in a fortnight's time on Thursday the 21st of May at 8 p.m. And we're planning to show some short talks by members of the Society on their home observing equipment. So we could still do with some more videos, so if you could submit those to us by the end of the week. Our June lecture is scheduled for Thursday the 4th of June, again at 8 p.m, and the talk will be by former Gresham Professor of Astronomy Ian Morrison from the University of Manchester, and his lecture will be on Southern Sky Astronomy. So on to this evening's meeting. Tonight we are really pleased to welcome to the Society Dr. Jeremy Shears. Jeremy is the Variable Stars Section Director at the British Astronomical Association, and he is also past president of the BAA. Jeremy is an active observer and astronomer whose main interest is in variable stars. He conducts his own research using CCD photometry of outbursts from dwarf novae from his own observatory at home. He's written several papers for the BAA journal on the subject. So, without further ado, it's my great pleasure this evening to introduce to you Dr. Jeremy Shears with his talk this evening on variable star astronomy and cataclysmic variables.
Thank you very much for the introduction, and it's a great pleasure to be with you today, and welcome to my observatory here in Cheshire. So tonight I'll be looking at variable stars, and during the talk I want to cover a number of different things. So we start off by considering why observe variable stars, what's so interesting about them. Then I'll touch on a little bit about the sort of equipment that you need. And then I'll spend a significant amount of time talking about 2 particular variable stars that you might like to observe tonight and over subsequent nights. And then towards the end of the talk, I'll move on to my own specific area of interest in variable stars. This is a group called cataclysmic variables. So I always like to start off by showing this animated image of a globular star cluster, because it reveals dozens of variables. You can probably see them blinking away there in this speeded up movie. These are called cluster variables, and they were actually discovered in the globular star cluster M5 by a BAA member many, many years ago, a century and a quarter ago, David Packer of Birmingham. And it just shows you how many stars are variable. And you probably know that even our sun is variable, but happily it's not so variable as to affect us, our life on Earth to any great extent. Actually, we're very fortunate that the sun doesn't go through some of the huge changes that some of the stars we'll be talking about tonight go through. We'd be in a very difficult situation if that were to be the case. So let's start off by thinking about why observe variable stars. I think for me, it's about fun. So for many of us, there's a great pleasure to be gained watching from night to night a particular variable star, see its brightness change, and wondering about the reasons why those changes are being brought about. And after a while, after following a star for a period of time, they become like old friends. And I guess like any old friend, you're keen to find out how they're doing. So going out each night becomes a matter of course. You want to see how they are tonight. Are they brighter, or are they a little bit fainter? So there are many reasons why the collection of data on variable stars is an important and useful activity. Research on these variable stars provides a huge amount of information that we can learn about stellar properties. Some of them are shown here: how bright the star is, how large it is, what its temperature is, and even something about its evolution. How far through its life cycle is it? Variable stars come in all kinds of guises, and some need to be observed over decades in order to be able to see their variations, but others change much more quickly, perhaps even over minutes, and we'll look at some of those stars tonight. At least for me, variable star observing becomes even more rewarding when professional astronomers request the data that we've collected, and they take it away for analysis And from those data, they deduce amazing snippets of information regarding the star or the system we've been monitoring. And the brightness measurements that we made on a star on a particular night may be the only observations that exist for that star at that specific time. So they could be really valuable. Professionals these days also don't have the time, nor do they have the telescope access to monitor every star all the time. And if a particular star does undergo some unusual behavior, amateurs keeping an eye on it can alert the professionals to what's going on. And that sometimes involves allocation of time being made to the professionals on world-class telescopes around the world, or even orbiting satellites in space. Professionals also request data from time to time at the same time as they're carrying out observations with their own telescopes, or perhaps even by satellites. So they want to know what the ground-based observer is seeing at the same time the satellite is observing it. So let's start with a recent example of a well-known variable star. I have to say, it's not often that variable stars are featured in the main news programs, but that did happen last December, and some of you probably saw the news bulletins, even on the main BBC 10 o'clock news, about the bright star Betelgeuse in Orion undergoing a fade. And one of the reasons why the media got so excited about it is that there was some speculation that Betelgeuse might be about to go supernova. Now, we have known for many years that Betelgeuse is what's called a red supergiant. So it's a massive star, and it's a star near the end of its life. And therefore, it's entirely possible that it will go supernova at some stage in the next, well, let's say 100,000 years. But I have to say that it's not connected to the recent fade. So Betelgeuse is easily recognizable as the right shoulder of Orion, and it's normally one of the 10 brightest stars in the sky. And it began to get a bit dimmer around the end of October of last year. And by mid-February of this year, it had lost more than 2/3 of its brightness, as shown in this animation at the top left by Tim Weatherall. So visual observers found that the star faded from about magnitude 0.5 down to about 1.7 in February, as shown as in this chart from the BAA variable star section. On the light curve, you can see the y-axis has the brightness of the star, or the magnitude of the star, and the x-axis has the date from last September until now. As you can see from the plot, there was the fade. It reached minimum sometime in late February, and as you can see from the end of the light curve, it's almost back to its normal brightness. We're just about to lose it from view, of course, because Orion is setting in the west not long after sunset. Now, we know that Betelgeuse is actually a pulsating star, and as it pulsates, its brightness changes. And there are a number of cycles of variation that Betelgeuse undergoes. There are two prominent ones. There's one about 400 days, and there's another one of around 6 years. And one of the reasons for this fade is that it's due to a coincidence of those different cycles. So you get a much dimmer minimum than you might otherwise get. But there's also something else going on, because if you look at the image at the top right, comparing January of last year with December of last year, this is an image taken by the Very Large Telescope in Chile. It shows in December there was a dusky area at the lower half of the star. This seems to be particles, large grains of dust that might have contributed even further to the dimming of Betelgeuse. I think what's clear from this observation is that astronomers are going to be guessing for quite a while about precisely what's going on. But the thing I'd like to point out is that these variations in Betelgeuse and the conclusions that were drawn from them were made by visual observations by amateur astronomers around the world. I say, if you want to know a bit more about Betelgeuse, there's an article in the current BAA Variable Star Section Circular, and you can download that from the BAA website. You don't have to be a member to do that. It's freely available to all. It's an article by Dr. Mark Kidger, and I highly commend that. So let's start thinking about the type of equipment that you might need. The first thing to say is that the beauty of variable star observing is that you can use whatever kit you've already got. You don't have to go out and buy a new instrument. You can even use the naked eye. We've just seen that with Betelgeuse, how important naked eye observations can be. If you move up to binoculars, well, they provide a lifetime's opportunities with the variables. And very roughly, there are two branches of variable star observing. One is visual observing, where you compare the brightness of a particular star with other stars in the same field, neighboring stars, who have a known brightness. The other is photometry using a CCD camera or perhaps even a DSLR camera. And here you take an image with one of those cameras, just like you would of a deep sky object, and you use software to measure the variable's brightness within that image. Some people use remote telescopes, many available over the internet. Other more advanced observers use spectroscopy, and others, yet again, getting enjoyment from analysing variable star data that have been collected by many observers over many years, and that's something you can do, of course, even when it's cloudy. So whilst variable star observers tend to observe alone, I think I should point out it is actually a team sport. So here we've got another light curve. Again, you can see the parameters on the y-axis as being the brightness of the star, the magnitude, in this case from 5 to 14. A fifth magnitude star is just above the limit of naked eye observation from a dark site. And on the x-axis, you can see the dates, the years, starting in the year 2000 to up to the present day. So these are data from taken by Sean Albrighton using binoculars. And you can see that there are a few gaps in the data. The more observers there are, the better quality of data and the more complete light curve you get. For most of us, you can't observe every night. It may be cloudy, you may have work commitments, you may have social commitments. So it's good that there are other observers that may be available that will be able to fill in the gaps. So let's look at how that might work out. So if we add just one more observer, and in this case it's Mike Gainsford from Leicester, and we had his observations to Sean's, you can immediately see there's more detail visible in the light curve from that greater coverage. But we're still missing significant sections. So what's going on there? Well, let's add another 53 observers, and the names are shown at the bottom there, very small. So if you see your name there, congratulations. You can see that we now have a light curve that's extraordinarily complex. And well, I'd even describe it as being rather beautiful or even exquisite. And we now see that it's the light curve of the first star I'm going to talk about today, which is in the Northern Crown. It's R Corona Borealis. So R Corona Borealis shows dramatic and unpredictable fades. You can see those here. They occur within a few days. You can see a sudden drop off in brightness there in about 2007. And sometimes those fades go down to the 15th magnitude. You need a pretty large telescope to see the star at that point. And then over succeeding months, they gradually recover to their original brightness. So that 2007 fade, in the middle of the plot, the star dropped around 8 magnitudes in only 33 days, so a real precipitous fall. And it was in a faint state for quite a few years after that. There are a couple of ups and downs there, but it's now almost recovered, although there was a brief fade, as you can see, last year. So what's going on with this star? Well, we have a lot of data going back to over 200 years on this star. for it was first discovered by Edward Pickett in the last years of the 1700s, and he was observing from Bath. Our Corona Borealis is known to be a yellow giant star. It's about 100 times bigger than the Sun, and it's what astronomers call a highly evolved star. And compared to most stars, its surface is actually very poor in hydrogen. Probably only contains 1% of hydrogen, and the vast majority of the rest, around 90%, being helium. And it's also rich in other elements, including carbon and nitrogen, as well as molecules such as cyanogen. And it's now thought that these fades are caused by the condensation of carbon soot, which puffs off into space, as was shown by the animation. I noticed it's just finished now. And that soot around the star makes the star fade in invisible light. However, if you were to continue to monitor the star in infrared, there's actually no significant real luminosity decrease, because the infrared light gets through those sooty dust particles. So eventually the dust disperses, and that re-exposes the photosphere of the star, and it returns to its maximum brightness. So our Corona Borealis, this sooty star, is the archetype of a small but very select family of stars known as the R Corona Borealis family. And there are only about 150 of those known in the galaxy. And the second brightest member of the family is called RY Sagittarii. And I always like to point out that was discovered by a previous variable star section director, Colonel Markwick, back in 1893. So let's talk about how you can go about observing our Corona Borealis. Finding it is actually rather easy, I'm glad to say. And the chart shows the sky as you'd see it about 11 o'clock tonight if you went out and looked towards the southeast. To locate the constellation of the Northern Crown, you need to, first of all, locate the bright star Arcturus. That's fairly easy to do, because if you can find the plough, look at the handle of the plough, the curve of that, if you follow that curve round, it will point you in the direction of Arcturus. And that's in the constellation of Boötes, the herdsman, which to me doesn't look like a herdsman at all. It looks more like a kite lying on its side. And just below that kite, you'll see the round circlet of the Northern Crown just nestling in there. So here's an enlarged view of the Northern Crown, and you can see R lying almost in the middle of it. It's currently just below naked eye visibility. However, it's easily visible in a small pair of binoculars. And as I said earlier, at a minimum, you'll need quite a large telescope to be able to find it. So if you wish to estimate the brightness of the variable, you need a chart such as the one shown here. And you can download these charts from the Variable Star Section's website. This shows the stars that make up the Northern Crown, and you'll also see scattered amongst them some fainter stars that you'll see in your binoculars. And the location of R is shown right at the center. You can probably see the little circle with a dot in the middle of it. And the chart also shows the brightness of a number of neighboring stars against which you can compare its brightness. Fortunately, it was clear here last night, and I looked at R with my 8x42 binoculars, and I had it slightly fainter than the star marked E on here, and I reckon it was about magnitude 6.7. So again, below naked eye visibility, but easily visible in my small pair of binoculars. It's definitely worth keeping an eye on, because only continued monitoring will tell us when that next fade is due. This attractive animation by Greg Parker of the New Forest shows that the star on two different occasions, once when it's about 14th magnitude, you can hardly see it, and then in a brighter state at the 8th magnitude. And I like this image because it's actually quite a photogenic field that R sits within. So that's the first star. Let's look at another one now. This is another famous variable in Corona Borealis, and this time it's called T. Now, T Corona Borealis is a very different star from R. And you can see it marked on the chart here. It's just outside the circlet of the crown. Now, normally this star slumbers at the 10th magnitude, as it was last night. But if we go back to May the 12th, 1866, it was spotted by John Birmingham of Tuam in Galway in Ireland as a new star or a nova in the night sky. And in its brightest, it was magnitude 2, so it was easily visible to the naked eye. And it briefly outshone the brightest star in Corona Borealis, which is Alphecca. You can see it on the chart there. But it then quickly faded back into obscurity. John Birmingham had only been introduced to astronomy a few years before his discovery, and he was enjoying the hobby. But flush with the success of discovering this nova, this new star, he went out to purchase a 4.5-inch refractor, which was a pretty hefty investment back in 1866, and later went on to become a leading observer of red stars. But the story didn't end there in 1866, for to move forward 80 years, on the morning of February the 9th, 1946, the nova actually sprang back to life. And it was discovered independently by 2 observers, one on either side of the Atlantic. The first was actually another BAA member, Norman Knight, who lived in Bedford Park in London. And then 2.5 hours later, it was discovered by Armin Deutsch. You can see Armin here. Armin was a graduate student at the Yerkes Observatory. But on this occasion, he didn't need the 40-inch refractor, which you can see above him there. He was able to spot the nova in outburst with binoculars, and it topped out at about magnitude 3. Now, famed American comet hunter and variable star observer Leslie Peltier faithfully kept an eye on T Corona Borealis for 25 years before this outburst, and he was really hoping that he would be the one to detect it in outburst. But sadly, on that fateful morning, he got up with the alarm at 2:30. He went to his window, pulled back the curtains. It was indeed very clear, but he wasn't feeling 100%. So he thought, well, I better go back to bed. I owe it to myself and my family not to go down with a cold. And I mean, I felt that like that on many occasions myself. But unfortunately for Leslie Peltier, it was a big mistake. For it was that very morning that T came back to life. And Peltier describes how he continued to monitor T for the rest of his life, but it was always with a very wary eye, he said. I've got shown a picture here of Leslie Peltier's autobiography, Starlight Nights. And it's the biography of one of the greatest amateur observers to live. And he lived in Ohio in a farm, but rather than describing about how he goes about observing stars, he actually describes his love of the night sky. I've recently reread it, and this time it had several resonances with me, because it describes, amongst other things, of how he was isolated in his farmhouse during the very cold Midwestern winters, and also during the Great Depression. And he describes that under all those conditions that his life slowed a little bit. The family and he withdrew into the farmhouse, but his astronomy continued throughout. If you haven't read this book, I can thoroughly recommend it. So T Corona Borealis, like all novae, is actually a binary star. It's made up of a red giant star. You can see it on the right there with the star spots. And that has a 227-day orbit around a tiny planet-sized white dwarf. And because that white dwarf has a strong gravitational field, material is drawn off the red star, and it accumulates around the white dwarf in this accretion disk. And some of that gas eventually gets fed down onto the surface of the white dwarf. And there it becomes compacted and heated, and eventually ignites in a spectacular thermonuclear runaway explosion. And what we observe is the sudden brightening of the star. And this is the nova eruption itself. And during that eruption, the outer layers are blown away into space, leaving a planetary nebula, a very tenuous sphere of gas around the system. But when a nova explosion occurs, only a small proportion of the star's mass is lost. And it's thought that some novae, perhaps even all novae, reoccur on different timescales, perhaps on timescales of thousands of years. There are only 10 novae that are known to have occurred, the family of recurrent novae, in our galaxy. Recently, there's been a recurrent nova discovered in our neighboring galaxy, M31, the Andromeda Nebula. And that holds the record of having the shortest recurrence time of all novae. It's around a year. And members of the variable star section have been monitoring that star in a pro-am collaboration with researchers at the Liverpool John Moores University. I have to say this is a very faint target to monitor. Normally, you don't see it at all. I don't see it in my telescope. And even when it goes into a nova eruption, it only reaches about the 18th magnitude. So it is monitored by amateurs equipped with very sensitive CCD cameras. So given the gap of 80 years between the two previous explosions, so 1866 and 1946, people have speculated that perhaps we're due for another eruption of T in the next few years. And the 80th anniversary, of course, falls sometime in 2026. So after the 1946 eruption, T effectively stayed under the radar for the next 69 years. It was pretty steady at magnitude 10.3, just a few ups and downs here and there. But that began to change back in February 2016. When it inched up to magnitude 9.2. So it's almost a magnitude brighter than it had been for many years before. And you can see the little blip there marked by the red arrow. Although this brightness wasn't sustained, it's still brighter than it has been during the previous 69 years. And as well as that brightening trend, T also has become bluer. And astronomers describe this brighter blue state as being a superactive state. And it's rather tantalizing to note that this last happened, it last underwent a superactive state back in 1938, 8 years before the last great outburst of T. So the question is, will T outburst tonight? Will we see an eruption tonight? Well, who knows? It may be tonight, it may be in the next few months, it may be next year or several years, who knows? But surely it's worth keeping an eye out for. At the moment, you'll need probably a small telescope to see it at around 9th or 10th magnitude. Something like a 3-inch refractor, 75mm refractor will show you T quite nicely. And again, if you want to record the star's brightness, simply download the charts from the variable star section website. Now, when it does go off, telescopes all around the world and those in space on satellites will be directed towards it, because we're going to learn a lot about nova eruptions from its next outburst. But bear in mind that when it does erupt, you won't actually have very long to observe it, because it's probably only going to remain a naked eye object for about 5 or 6 days based on the last two experiences. So novae, like T Corona Borealis, are the most dramatic examples of a class of stars known as the cataclysmic variables, or CVs for short. And I'll refer to CVs as we go forward. Now, these CVs, as I've intimated before, are actually binary stars containing a white dwarf. So this is a very small planet-sized, highly dense star. And then there's a secondary star in orbit around it. This is usually a red dwarf, much smaller than the one in T Corona Borealis. And the whole system is really compact. For most cataclysmic variables, you could fit both stars in the Earth-Moon orbit. They're literally that compact. And as we saw with T, because of that strong gravitational field that the white dwarf has. It's drawing the gas off the red dwarf, and it spirals in towards towards white dwarf via this accretion disk. However, in some cases, the white dwarf is very magnetic, and therefore you can't get an accretion disk forming. So you simply get this chimney of material flowing from the red dwarf onto one or other poles of the little white dwarf there. And that inflow of material follows the magnetic field lines of the white dwarf, and it impacts on the poles of the star. So that's a very magnetic star. Well, you can get intermediate situations like the one shown in the bottom left here. This is where the white dwarf has not quite such a strong magnetic field, and here you still get an accretion disk, but it's truncated. The middle bit is cored out by that magnetic field from the white dwarf. And what I find interesting about cataclysmic variables is that they vary on a wide range of timescales, and these can be from seconds to decades. And that's really, for me, what makes them so interesting. Of course, it's the outburst when a star suddenly brightens. That's the most sought-after events. And in the case of a nova, the brightening can be, say, 10 millionfold. And that was the case with T Corona Borealis. And the cataclysm is caused by the material being ejected into space by that thermonuclear explosion. By contrast, the dwarf novae, another type of cataclysmic variable star, they're less flamboyant, and here the brightness is only around 100-fold. And the origin of this much more modest cataclysm is in the accretion disk itself. And what happens is that as material builds up in that accretion disk, there's a thermal instability. The disk can't process the material fast enough, so it gets hotter. And as it gets hotter, it becomes brighter. And that's what we see as the outburst of a dwarf nova. So what links cataclysmic variables together is this phenomenon of an accretion disk. And as you may know, accretion is one of the fundamental properties in astrophysics, or physics in general. And one of the reasons for studying cataclysmic variables is to study accretion disk physics and learn more about what's going on. Accretion disks occur in a number of different astrophysical situations. For example, during star formation, a star will condense out of a rotating interstellar dust and gas cloud, and there'll be an accretion disk formed at that point. And the remnants eventually coalesce, and planets form as a result of that. And that's probably how our solar system formed a long time ago. On a larger scale, galaxies are initially formed as gaseous accretion disks. And another example of an accretion disk is in what you find around a black hole. And I'll talk about black hole accretion disks a little bit later in the talk. So studying accretion disks around black hole binaries or black holes, and studying accretion disks in early stellar systems is clearly observationally very, very challenging. In the case of our own solar system, it's impossible. So astronomers like to use the accretion disks in cataclysmic variables as a proxy to understand what's going on. Amateur astronomers, including members of the BAA variable star section, have contributed to CV research for well over a century. And probably the most famous dwarf nova of all is SS Cygni, the one shown here. It was discovered back in 1896. And this star spends most of its time at around 12th magnitude, but every couple of months or so, it suddenly brightens to the 8th magnitude, where it stays for a few days before fading back slightly more slowly. We now know, having studied many of these outbursts, I don't think we've missed one since 1896, what we've learned from those studies is that, like all dwarf novae, these outbursts are only quasi-periodic. You can't set your clock by them, so you can't really predict when it's going to happen with any certainty. And it was the long-term light curves, such as the one you can see here for SS Cygni and its brethren, that catalyzed the modelling of what goes on in a dwarf nova outburst by professionals over many years. So SS Cygni is definitely one to follow. You can see it in a relatively small telescope. With Cygnus coming back into view, it's something you might like to start observing, and of course you'll be able to follow it well through into the autumn, perhaps even into next winter. Professionals are keen to hear about outbursts of SS Cygni, because quite often they ask to be alerted when there's an outburst, because they want to carry out other observations or observations in other wavelengths. And over the last few years, I think we've received more than a dozen requests for assistance in monitoring these stars to support radio observations by the E Merlin network and also the European Very Large Baseline Interferometer. So that's another example of pro-am collaboration within variable star astronomy. So one of my own observational programs is to patrol for these outbursts of dwarf novae, but I particularly focus on those that aren't very well characterized. Perhaps they've only been recently discovered, so we don't know how often they'll go into outburst, or even in some cases whether they will go into outburst. So spotting the first outburst of a newly discovered CV is actually quite exciting. I use a C11 telescope. You can see it in the middle there in my observatory in Cheshire. My observations are exclusively with a CCD camera on the back. On the other hand, Gary Poyner, you can see on the left, he lives in Birmingham, and he's a dedicated visual observer, and he has a half-meter telescope. So that's another style of observing. And then Paul Leyland on the right is lucky enough to live in the Canary Islands, where he has a 0.4 meter telescope with a CCD camera on the back. So what I do night after night is visit many fields of these CVs to see whether they've suddenly come into outburst. And once an outburst has been detected, I let others know, and that's usually by email, the number of email lists, to get the message across the world. And that enables people around the world to start getting more data during the course of the outburst, because often these outbursts only last a few days, perhaps a week, 2 weeks at most. So there's a limited time during which we can get data. And I think the recent developments in astronomy, people with larger telescopes, more sensitive instrumentation, are really working with professionals in some very strong collaborations. And it's quite often the case that the professionals and amateurs will jointly write papers together on the findings. So one area that has received a lot of attention is in kind of dwarf nova called an SU Uma system. So SU Ursa Majoris is the archetype of this particular kind of dwarf nova. But what differentiates SU Uma systems is that when they go into what's called a super outburst, they're even brighter than a normal outburst, so about half a magnitude brighter. And if you monitor very carefully the brightness of the star, you'll see tiny little modulations, little variations, as you can see in the bottom of this plot here. And those little humps are rather grandly, or should I say grandiosely, known as super humps. And these super humps are caused by an interaction of that accretion disk with the secondary star orbit, so that red dwarf. So you have an elliptical disk. This disk becomes elliptical. You have a modulation, and that's what gives rise to these super humps. And you can see in this plot here of a star called V404 Cygni, which incidentally went into outburst last week. And you can see its associated superhumps. And if you measure the period of those superhumps, and the period, each hump is typically around, say, 2.5, 3.5 hours, you can learn a lot of information from the superhump period. Because it gives a really good idea of what the orbital period of the system is. So the orbital period of that red dwarf around the white dwarf primary. And if you know the difference between the orbital period and the superhump period of the star, you can then find out what the mass of the secondary, or the mass ratio of the secondary to the primary is. And with that mass ratio, you're already beginning to build a picture of that little binary system, that tiny little binary star system. Another hotly debated subject in astronomy is what causes these super outbursts. And what's been seen, again, largely from amateur observations, is that usually a super outburst appears to be triggered by a normal outburst. The trouble is that rather few of these precursor outbursts, we saw one in V404 Cygni, as you can see marked on the plot here, very few of these precursor outbursts have been spotted. So one of the programs that we have is to try and spot precursor outbursts. Now, these photometric campaigns are really something that amateurs are geared up to do, because what happens is that you usually find a group of amateurs around the world club together and keep an eye on the star as long as possible while it's in its bright state. And the aim is to get as near as continuous coverage during that week or two of the outburst as possible. And you can do that by having observers located around the world at different longitudes, but also in different locations that maybe it's not everybody's going to be cloudy at the same time. So having observers located around the world is a real advantage. So if you remember earlier, I talked about these stars, these CVs, in which the white dwarf has has a magnetic field, but it's not a particular strong one. It's not so strong that it disrupts the accretion disk significantly. So you'll still get a disk, but it's truncated. The inner part's missing. And these stars are known as intermediate polars. And in these intermediate polars, the white dwarf, the little star at the center of the magnetic field lines there, rotates about 10 times faster than the orbital period of the red dwarf system. And the typical spin period is only a few minutes. So imagine that white dwarf spinning around very quickly every few minutes. Measuring those spin periods of intermediate polars has become a popular sport for amateur astronomers. And in fact, there's an organization that's pretty much dedicated to making these measurements. It's rather grandly known as the Center for Backyard Astrophysics, and it's run jointly by Joe Patterson at the University of Columbia, and Enrique de Miguel at the University of Huelva. And keeping time on these intermediate polars is definitely a long-term project. And you really need persistence and patience. And because of the telescope time involved to aggregate all these observations, it's largely this responsibility falls to amateur astronomers. So now I want to touch on a rare class of cataclysmic variables, and these are the helium dwarf novae. And they're sometimes called the AM CVN systems after the archetype AM Canaan Venaticorum. These are also accreting binary stars, and they, as with the other CVs, they contain a white dwarf. But this time, the secondary is a helium-rich star. So it's a very highly evolved star. And these really are ultra compact systems, and the orbital period of one star around the other can be as short as 5 minutes up to about an hour. So they're literally whizzing around each other. And they're rather rare. So by contrast to their hydrogen-containing customers, where several hundred or even a few thousand known, there are only a few dozen helium dwarf novae currently known. And once again, amateur astronomers equipped with small telescopes and CCDs can do useful work in conducting time-resolved photometry, so monitoring the brightness over time during an outburst of these systems. And a few years ago, one of these particular stars went into outburst, V404 Andromeda, and during its outburst, we found these super humps. So we confirmed it was a super outburst of the system. And by carefully measuring the period of those super humps, we worked out the orbital period of the secondary around the white dwarf is something of the order of 37 minutes. So it's the first time that orbital period had been measured, and that was based on amateur observations. So I said they're quite rare. There are fewer than 60 helium dwarf novae known, but there are quite a few being discovered almost day by day now, because there are a number of sky surveys that are up and running, like LSST and Gaia. And a recent discovery gives a hint of some of the exciting times ahead. There's a diagram here of the system Gaia 14AAE, fortunately had rather obscure names. This was observed to be an outburst and followed by an international team of amateurs and professionals led by Heather Campbell at Cambridge University. And we found that it was actually an eclipsing system, and it's the first helium dwarf nova in which the white dwarf was found to be totally eclipsed. And that was a result of amateur observations. So until now, we've considered binary systems which contain an accreting white dwarf at the center, and it's the gravitational pull of the white dwarf that draws material away from the center. However, there's an even more exotic class of binary system in which the accretor at the center is a black hole. And some of these systems undergo outbursts similar to those that we see in dwarf novae, in which the accretion disk brightens and sometimes even shows these super humps. And one of the systems is the one that we have been showing the movie of here, V404 Cygni, and that contains a 17 solar mass black hole with a red giant star in a 7-day orbit around it. And back in 2015, it was found to be an outburst by NASA's SWIFT satellite. And the detection by SWIFT triggered hundreds of instruments to point towards it, including amateur observers. And the results of those observations were published in the scientific journal Nature, probably the most prestigious scientific publication of all. And that paper included photometric observations by a number of amateurs, including BAA members. So I've only been able to cover a few different examples of the kinds of variable stars in this talk today. There are many others, as I've said, and if you'd like to find out more about them, more about the work of the variable star section, how to observe variable stars, then do visit our website. The address is shown at the top of the slide here. The BAA VSS is actually the oldest organization for variable star observing. It goes back to 1890, formed in the same year that the BAA itself was formed. The section can provide ideas about which stars to observe. It can help you put a program of stars together, whether you're a visual observer or a CCD observer. We have a mentoring scheme. So if you want to start out observing variable stars and you're not quite sure how to go about it, or you're not quite sure of the quality of your data or what the results mean, then we can put you in touch with a mentor that can help you up that learning curve. We supply charts. Charts we've seen already for our Corona Borealis, but many other stars are available from the website. And every 3 months we publish a circular with up-to-date information about what's going on in the world of variable star astronomy. And I mentioned earlier the article on Betelgeuse in the current circular, which I highly commend. From time to time, we organise observing campaigns on specific stars. And we also organise meetings, although of course those are in abeyance for the time being. Hope to get back to those soon. So I hope this talk has given you at least some indication as to the way that amateur observers can contribute to the broad area of variable star astronomy. I feel I've only just been able to scratch the surface, though, in the examples I've provided. I do hope it might have stimulated some of you to go out and look up at the sky, look out for our Corona Borealis. Has it begun its fade? Is it still around 6th magnitude? To keep an eye on T Corona Borealis. Is it still 10th magnitude, or has it started its eruption, by which time it will become a naked eye star? And perhaps even to follow the dwarf nova SS Cygni. So whatever type of observing you like to do or equipment you have available, naked eye, binoculars, telescopes, CCD, there's a variable star opportunity out there for you. And with that, I thank you for listening, and I'll open the floor to questions. Thank you very much.
Well, thank you very much indeed, Jeremy, for that really interesting talk. And it's great to see an area of astronomy that amateurs can contribute to. So we've already had quite a few questions come through during your talk. So I'm just putting those on the screen now. So hopefully you'll be able to see those in a minute or two.
Okay.
Before we kick off with questions, and just a reminder to everyone, if you want to submit your questions, please do so using the YouTube live chat facility. We do actually have a 30-second delay on the YouTube feed going out, so start putting those through now, and we'll start answering those. So can you see those questions on the screen, Jeremy, or do you want me to read those through?
No, I can see them, Richard. So I'm just reading through the preamble. So there's a question there about calculating the magnitude of a variable star using a CCD camera. Actually, I'm pleased to say this is a relatively easy thing to do, thanks to really cunning software that's available. There are a couple of packages that people generally use. There's one called AIP for Win, which is Astronomical Image Processing for Windows. And there's another one called Astro Image J. And basically they serve the same function. All you need to do is to import one of your CCD images into the program. You tell the program which is the variable star. In other words, you click on it. Then you click on a star that is of a constant brightness, a comparison star. And the software will automatically work out by interrogating each pixel how much light has fallen on the pixel. It will integrate, and it will then work out the difference in brightness between the variable and the comparison. And through a bit of background calculation, which you don't have to do, the program does it, it will tell you the brightness of the star. You normally identify a third star in the field, which is a check star, again, another star that doesn't vary, just to make sure that it is indeed constant throughout the analysis that you're doing, in case maybe clouds or something else interferes. The next question is about the animations. Some of them have spots. Some of the stars have spots on them. So these are the star spots that occur on typically on the red dwarf that's going around this white dwarf. And if you remember, the white dwarf is pulling gas off the red dwarf through its gravitational field. So you get this flow of material off the red dwarf. And that will continue indefinitely until if there happens to be a sunspot on the red dwarf, and many of these red dwarfs are believed to have sunspots or star spots, if a spot goes underneath that flow of material, it will actually cut off the flow of material, and that will mean that there's no more new material coming into the accretion disk, and it's the accretion disk that's the bright part of the system. So the star will fade, and it will go into a minimum, and that will continue until the star spot moves off. It rotates away, and then the accretion will start again. So, looking for those periods when the accretion stops is also really valuable. It's not just the outburst. Sometimes when the star goes really faint, too faint for amateurs to observe, but that's when professionals also get really excited, because without that accretion disk, the professionals with their huge telescopes can probe the nature of the white dwarf itself, which is usually drowned out by the accretion disk. So there's a question here about novae, whether they're it's the red giant and not the white dwarf. So in fact, in a nova explosion, so these are the really bright eruptions, this is actually a thermonuclear explosion of material on the surface of the white dwarf. So the material has gone through the accretion disk, and it ends up on the white dwarf. And usually the white dwarf will absorb it in some way, but under certain conditions, it will continue to build up until there's such a lot of it there that it undergoes a thermonuclear explosion, and it's that causes the nova eruption, and that will take place over a matter of hours or perhaps a day, and that's what causes the star to brighten. So that's the nova. Just to recap on the dwarf nova, that's a much less dramatic but nonetheless interesting event. There, the brightness is not a thermonuclear explosion. It's the accretion disk itself brightening, and that's because the disk can't process the material sufficiently quickly. It becomes viscous and really hot, and it will brighten, and eventually it will cool and go back to minimum. Any more questions? I think I'm down.
I think that's all the ones we've got so far. I've got one, if you don't mind me asking.
Yeah.
Any tips for amateur actual visual observers how best to estimate magnitude of stars and also when they're dimming? So we saw it with Betelgeuse over the winter. Is there any good tips to actually how to measure that visually? Yeah.
When you describing how to make a visual observation always makes it sound much more difficult and complex than it is in reality. It's actually a very simple thing to do. You will need one basic piece of information, and that is a star chart that shows the variable star, Betelgeuse, for example, but also a number of comparison stars that are nearby. And in the case of Betelgeuse, because it's a bright star, there'll be stars in the neighboring constellations, so a fair distance away. And then and each of those stars is of a known brightness, so a known magnitude. And then it's a simple matter of looking at Betelgeuse and then comparing it in turn with each of those comparison stars until you find a comparison star that's a little bit brighter and one that's a little bit fainter. And therefore you know that its brightness is somewhere between those two stars. And then it's a little bit of mental agility, because if you have the fainter star and the brighter star, you can mentally divide the distance in brightness into say 5 units, and you might say that tonight Betelgeuse is one of those 5 units brighter than the faintest comparison star, and 4 units fainter than the brighter one. So it's between the two, but it's closer to the fainter one. And knowing the brightness, the magnitude of the stars, comparison stars, which is on the chart, quick calculation will show you what the actual brightness is. So it is relatively simple, and that's a naked eye observation, but it's exactly the same process if you have a binocular. So if you're looking at Arca and Borealis, you find the star in your binocular, sitting in the middle of the northern crown, and then you look at stars in the vicinity until you find one slightly brighter, one slightly fainter, and then you can do the same trick, if you like, of working out its brightness.
You got another question in there. Says if there is,
got it. Yeah. If there's one, if somebody wanted to start observing, if there's one star that you recommend to observe with a small telescope, which is the easiest? For me, there are two aspects here. So it depends what you mean by easiest. So ease of finding it is one thing, but for me, an equally important one is whether the star is going to actually be interesting enough for you to continue to observe. So I would like to recommend stars that change quite quickly to people that are starting out, because then they got a good chance of actually seeing something changing within certainly a few weeks, if not a few days. And one of the best starting stars is actually one of the ones I talked about this evening, only in passing though, which is SS Cygni. So in the constellation Cygnus the Swan. This is one of these dwarf novae, and it varies between 8th magnitude and 14th magnitude. So it spends most of its time around the 14th magnitude. But when it goes into outburst, it is even detectable by binoculars. But a small telescope, you can see, say, a 3-inch refractor, 6-inch reflector, 5-inch Mach. You can follow most of the cycle, and it will go off into one of these outbursts every few weeks. So if you were to start observing it tonight, given that Cygnus is already appearing in the east not long after sunset, you could follow it through, well, even through into January next year. So how long is that? 9 months or something like that, 8 or 9 months. You're going to experience several outbursts in that period, in that interval. So that SS Cygni is a good one to follow. I see there's another question. In one of those close binary systems, might the star that eventually became the white dwarf have previously gone through a giant phase in which it enveloped the red dwarf? Yes. So this is a really interesting question about about stellar evolution, but also how these close binary systems form. Just to remind you that many of these are so small they could fit in the Earth-Moon distance. And indeed, at one stage, one of the stars probably encompassed the second star, and you have this common envelope, as it's called. A white dwarf is obviously a much more highly evolved, an older star. It's gone through the vast majority of its life than the red dwarf. So the two stars will have lived their lives at different rates. And trying to understand how that happened is one of the research questions within cataclysmic variable star astronomy. It's even more interesting when you consider that in some really exotic systems you can actually have two white dwarfs. So you have a binary white dwarf, and there's a huge debate as to whether those white dwarfs formed from younger stars that were in close vicinity, or whether they actually formed independently and captured each other. So there are favoured theories, but I would say not all has been said on this subject yet.
Cool. I've got a question. I noticed from your talk your C11's attached to a CCD camera.
Yeah.
How easy is it to do with the DSLR, and what are the advantages and disadvantages of using a CCD to a DSLR camera?
Yes. So I mean, couple of ways I could answer that question. So let's just put to one side at the moment putting the DSLR on a telescope. Many people have DSLRs that enjoy taking pictures of the night sky, and you can use the same process without a telescope to do variable star astronomy. And one of the advantages of DSLRs is that they're much more precise than the eye. So you can get much more precise measurements out than the visual astronomy. You can get about 1/100th of a magnitude accuracy from a DSLR, whereas a visual maybe 1/10th of a magnitude. And that means that you can target stars that are that vary, whose variation is much smaller than the eye can detect. So a DSLR on its own is a superb instrument. And then it becomes even more interesting when you put it in on the back of a telescope. And there it's really the same discussion point as to whether it's better to have a DSLR or CCD for conventional imaging. One of the advantages of a CCD is that generally these are cooled, so you have less noise in the system. Noise is a kind of bugbear in any kind of digital photometry. If you can reduce the noise, then your signal becomes easier to detect, and the signal is the variable star. So there are advantages in using CCD cameras, especially when you want to get to some really faint stars that require long integration times. So an 18th magnitude star, you might need to integrate for say 1, 2, 3 minutes, and the CCD has the advantage. It's because of the cooling, there's less noise in the final image, which means the photometry is better. But these are getting really into niceties now. Use what you've got is the simple answer. Yeah, DSLRs are great. Online question: can you observe variable stars in other galaxies? Yeah, that's a good question. So the most obvious variable stars in other galaxies are, of course, supernovae. You might not describe those as variable stars, but they do vary. So yes, you can observe supernovae in many external galaxies, and the BAA variable star section does follow supernovae. Similarly, there are some galaxies that are close enough where we can actually see novae occurring. M31 is a classic one. In fact, there is one BAA member who specifically goes out to detect novae in M31 in the Andromeda galaxy, and has been successful over the last few years. But then there are other kinds of stars that were discovered as variable stars. An example being W Comey in the constellation of Coma Berenices. And people thought that was just a typical variable star. It looks like a point source, but in fact it turns out to be a quasar. So it's a kind of galaxy in its own right. So yes, you can observe whole galaxies that vary. And there's one that's quite topical at the moment. There's an object in Cancer called OJ287. And this is an active galactic nucleus. So it's effectively a galaxy. It's a very peculiar galaxy, shall we say. And that seems to have what astronomers believe is a binary black hole. So two black holes, one orbiting another. And as these black holes orbit, they churn up material, and that causes the whole of the active galactic nucleus to change in brightness. And amateurs have contributed to observing OJ287 for many years. And in fact, coincidentally, there's an article on the front page of the BAA website on this star right now, because professionals last week published an important paper about it. So OJ287, it's normally around the 14th magnitude. So a telescope with small medium-sized Newtonian telescope with the eye can follow that quite nicely. CCD, it's very easy.
Brilliant. I think.
And I've just got
Paul Leyland there.
Yep, just seen Paul. Hello, good evening, Paul. Yes, Paul is a keen observer of variables in other galaxies, and he's pointing out that there are a couple in M31 that he's following: AE Andromedae and AF Andromedae. And he's also moving on to M33 to start observing stars in that galaxy as well, which is great to hear.
Okay, I think that is most of our questions, so we'll let you go. Thanks once again, Jeremy, for a brilliant talk tonight. I know you've been in demand for many other societies, so we're delighted we got in there first. Don't have to wish you a safe journey back to Cheshire because you're already there, but I do see it's clear skies here tonight, so I bet you're out observing this evening. I'm
looking forward to getting out into the dome and seeing what's up. Excellent. Brilliant. Good to speak to you, Richard. Good to speak to you, everybody in Nottingham AS. Best wishes.
Thanks, Jeremy. Thank you.
Thank you. Bye-bye.
Bye. Okay, before we finish then tonight, just a quick reminder that our next meeting is on Thursday, the 21st of May. That's at 8 PM online. And that's going to be backyard astronomy. So various members have been out doing videos of their observatory setups. So we're going to play all those on Thursday, the 21st. So I hope you can all join us there. If you've got any more videos, please do submit those to us and we can get those ready for the evening. So I thought we'd finish tonight. Our last meeting that we held was on the planet Venus, and we'd got loads of really good images sent in by members of the Society to the Journal. So I thought we'd just end this evening by playing those images. So thanks all for joining us. I hope you have a very pleasant evening.